Okay, so in the previous analysis video, we proved that the maximum and minimum of two Riemann integrable functions is Riemann integrable. Well, we did not actually prove the minimum case, but we made the remark that the minimum case, it follows from the maximum one and some algebra. We are going to address these things when we solve exercise problems. Now, a corollary can be immediately derived from that maximum minimum result. So, let us first see this corollary. It has a name also. It says that absolute values preserve Riemann integrability. And it starts off like how these results start off. With a bounded interval I, and you have a Riemann integrable function f defined on I, real valued of course. Then the positive part of f defined like this, which we denote by f plus, and this is the maximum of the function f and the constant function 0, is also Riemann integrable. Obviously, because we have already proved in that result that the maximum of two Riemann integrable functions is Riemann integrable. F is given as Riemann integrable, and the constant function 0 of course is Riemann integrable. So their maximum, which we are calling the positive part of f, is also Riemann integrable. Similarly, their minimum is also Riemann integrable, which we denote by f minus, and we are calling it the negative part of f. Once you have these two things, obviously their difference is also going to be Riemann integrable by our original properties of Riemann integrability, I mean the first ones. And that is why this is also Riemann integrable. There is essentially nothing to prove in this corollary except for one thing. You need to make sure that this identity is true. You do know what this absolute value of f means. It's actually the composition of the function f and the ordinary absolute value function. What you have to do is you take any x in I, okay, evaluate this left hand side function at x and the right hand side function at x and show that the two results are equal. But you have to do it somewhat carefully. There will be two cases depending on whether the f value at that x is non-negative or negative. In other words, whether f of x is greater than or equal to 0 or less than 0. Depending on that, the values of the f plus and f minus will come and give you the right hand side. And depending on those same conditions, you can also calculate the value of the left hand side function at x. So I leave the verification of this identity to you. And let's now go to the next result, which is the main result. It says that the product of two Riemann integrable functions is also Riemann integrable. We have so far not talked about products. We have only seen sums, difference, multiplying an integrable function by a constant. Such things we have seen. Okay, so let's next see product. And this is going to be a theorem. This is in fact the last result of this section. Theorem 11.4.5. Products preserve Riemann integrability. And the statement is very easy. In fact, you can state it yourself. let I be a bounded interval and f from I into R and g from I to R be two Riemann integrable functions. Then their product fg, which is also a function from I to R, is also Riemann integrable. Next we are going to see the proof, but this proof, like that maximum minimum of two integrable functions, is going to remain incomplete. There it was incomplete because we did not exactly say how the minimum of two integrable functions is integrable. Here also there will be some gap, and these gaps will be filled in when we solve the exercises. Okay, so they will be addressed. It's not that we are going to just leave them. So let's start the proof. In the proof, we immediately make use of the positive and negative parts of these two functions, f and g, that come from the previous corollary. We have, now I am going to write two identities which one can write using that positive and negative part, and g equal to g plus g minus. The question is how these identities are true. This also you have to verify. Okay, it's very easy. It's in fact easier than proving that the absolute value of f is f plus minus f minus. So just like that you can prove this one also. It's very easy. You just have to calculate the left hand side function at any input and the right hand side. You will just see from the definitions of f plus and f minus itself, you will see that when you start with this, that's what I suggest. You start with this, there will be conditions based on whether your f value at x is non-negative or negative. Again, same thing. You will see that the result ultimately is f of x, irrespective of the condition. Similarly, you have this one also. Alright, now let us use the previous corollary and say that these individual functions are Riemann integrable, because that's what the corollary says now. By corollary 11.4 f plus f minus g plus g minus, these are all Riemann integrable. Now, our aim is fg. Now, let's calculate the product fg in terms of these individual functions. times g plus plus g minus. So f plus g plus plus f plus g minus plus f minus g plus plus f minus g minus. So we see that our function fg is the sum of four other functions. So it's enough to show that the four functions above g minus f minus g plus and f minus g minus are all Riemann integrable. Why? Why is that enough? That's because once you show that these are all Riemann integrable, then by our previous result, which says that the sum of two Riemann integrable functions is Riemann integrable, you apply that again and again and you get that fg is Riemann integrable. And this is where the incompleteness of the proof in the text comes. That's because the text only proves that f plus g plus is Riemann integrable and simply remarks that the integrability of the other three functions can be similarly shown. And fortunately, we do not have to work for the other functions from scratch. Just like that minimum case, which I remarked can be obtained from the maximum case itself, here also luckily, it follows, if we do some tricks, that integrability of this itself implies that these are also integrable. Exactly how, that we will see when we solve exercises. We are just going to see today that this is integrable. These are all Riemann integrable. So I don't think I have to again write that we will only see that this is integrable. That's understood. Okay. All right. So now the proof really starts by choosing epsilon. That's how many things start in analysis here also. Choose any arbitrary positive real number epsilon. Oh, okay, hold on. I think I am forgetting something. Before choosing epsilon, I mean, you can choose epsilon here also, but before that, something needs to be said about these two functions, f plus and g plus. You see, they are Riemann integrable, which comes from that previous corollary, which means in particular that they are both bounded functions. Additionally, they are non-negative also. They never take on negative values as outputs. Why? What is the definition of f plus? It is the maximum of f and 0, right? So if you calculate this at some point x, then it's going to be this, 0 of x. Do not forget that this 0 is actually the 0 function whose value is constantly 0 at every real number. This 0, however, is the real number 0. If it looks somewhat confusing, you write one more step like this, and then you write this, so that now you clearly know that this is the real number 0. This is the output of this function at the input x. Now there are obviously two cases. case 1 is when f of x is non-negative, right? In that case, what is the maximum of these two? Obviously f of x. So in that case, the max is going to be f of x, and f of x is greater than or equal to 0. So the output is non-negative. But there is a second case also where f of x is negative, it's less than 0. In this case, the maximum is going to be 0, still not negative. And that is why in any case, f plus always takes on non-negative real number values. And that's what we are now going to use by simply writing this. Since f plus and g plus are both non-negative, well, the text writes positive, but that's not exactly correct. The f plus value can be 0. Both non-negative and bounded there exist, because of the boundedness, there exist real numbers m1 and m2 such that these inequalities are true. 0 less than or equal to f plus of x less than or equal to m1 and 0 less than or equal to g plus of x less than or equal to m2 for all x. Non-negativity, boundedness. Boundedness actually in general means bounded from both above and below, but because 0 is already a lower bound, so we need not write minus m1 on this side. For all x in the domain. Okay, now we choose epsilon. And after choosing epsilon, we are going to write two inequalities which will remind you of similar inequalities we wrote in the proof of that maximum minimum, that theorem. Okay, so let me first think what I am going to write. Yes. Then there exist PC functions f plus underscore from I to R and f plus bar from I to R such that f plus underscore minimizes f plus and f plus bar maximizes f plus. Instead of writing these words, we can also write it mathematically such that like this, f plus underscore at x is less than or equal to f plus at x, which is less than or equal to f plus bar at x for all x belonging to I, and what? And such that some inequalities are true which involve integrals, and we have to be careful here. We already know that the function f plus is integrable, right? So its integral is also equal to its lower integral, right? Now, what is the definition of lower integral? The lower integral is the least upper bound or supremum of a set. What do we have in this set? In this set, we have integrals of piecewise constant functions that minorize f plus. So this is the least upper bound. Now, if you subtract epsilon from this, it will become even more less. Okay, it will become less. I mean, this quantity is less than even the least upper bound, so can no longer be an upper bound, and that is why subtracting epsilon from this means subtracting epsilon from this. It will no longer be an upper bound. This is no longer an upper bound of that set where the elements are integrals of minorizing functions. So there will be at least one such element which will exceed this, simply because it's not an upper bound. The corresponding function is this minorizing function. Say, at least one such minorizing function can be obtained for which that happens. So that is why we chose this minorizing function. And similarly, this integral is also equal to the upper integral of f plus, which by definition is the greatest lower bound of another set. And in this set, the elements are integrals of piecewise constant functions that majorize f plus. Now, if you add to this greatest lower bound epsilon, then it becomes even greater. So can no longer be a lower bound of this set of integrals of majorizing piecewise constant functions. Can no longer be a lower bound, which means what? It means that there will exist at least one piecewise constant function which majorizes f plus and whose integral is going to be less than this, because this is the GLB and this is even greater than the greatest lower bound, so is no longer a lower bound. So something can be less than this from that set. Okay, so that's how we have these two things. But next comes a subtlety, a complexity. There is no problem with this f plus bar. Why? You see, you remember that in the beginning itself we said that f plus is non-negative. And that is why this f plus of x, no matter what x is, where x is coming from I, this is non-negative. Automatically this is also non-negative. However, this may still be negative. Who knows? We have to prevent that. And to do that, the author next wrote this. Well, I hope I am not lost. The biggest danger is forgetting something crucial. Now, I think I have got all the things here. Oh, and one more thing, if you think that I have everything written here, that's not true. In fact, that's a wastage of time. No, we should not write each and everything. I mean, even when you say something in front of someone, you should not write each and everything. You just write key points, maybe lemma number, corollary number, these things, and the main points. The rest you have to produce from your understanding and memory. Okay, so that's how it should be. But of course, you can just simply look at whatever you have written and simply copy it on board. That is as good as not doing anything. Okay, that's a very bad thing. If I mess up here, then I have to rectify it here itself. And it happens. We saw that many times. That's okay, but copying something from somewhere blindly, that's nothing. Okay, that's just a wastage of time for you and also for me. Alright, so next week, we are going to write about the problem that this may be negative. Note that f plus underscore may be negative at some x in I. But we can replace f plus by this function, maximum of f plus underscore and 0, since this function is still piecewise constant and still minorizes f plus. But the question is why? How? That we have to answer. Which is piecewise constant minorizes f plus and has integral still greater than, we are talking about this one, no? And its integral needs to be greater than this, and the integral is still greater than this. But how? Let us see. So the first comment we are making about this function is that it is piecewise constant. Well, it is. You see, when we studied piecewise constant functions, there we came across a result which gave us the fact that when you add two piecewise constant functions, multiply take difference, these are all piecewise constant, and there if you go back to that statement you will see that the maximum of two PC functions is also a PC function. This is already a PC function and this is also a PC function because it's in fact constant, so obviously also piecewise constant, and so their maximum is also PC. So it's not a very big problem that this is a PC function. But then we say that this still minorizes f plus, just like the original function f plus underscore. Is that true? Let us see. Let x be any element in I. Okay. Now, why did we start doing this? That's because f plus underscore may be negative at some inputs. Let's consider first the case where it is not negative, it is non-negative. Let f plus underscore at x be non-negative. Then what is this function value at x? By definition, this is the maximum of this and real number 0. Due to this inequality, this is just this. And already this one minorizes f plus. So this is less than or equal to f plus of x. So fine. The value of this function at x is also less than or equal to the value of f plus at x. Let us next see the other case. I do not want to do anything here yet. Okay, so let me just change this itself. Instead, if you have this, then what will happen? Then this is negative, so the maximum is 0. Again 0 is less than or equal to this. Why? Because f plus is itself non-negative. So you see that no matter what your x is, just like the original f plus underscore, this max also minorizes f plus. But why are we choosing max? Because max, besides being PC and minorizing f plus, is also non-negative, not like f plus underscore, which has a possibility of being negative at some places. This one is non-negative because it's the max of another function and 0. Okay. And what about the last remark? That its integral is still greater than this. Well, that's very easy. Just from the definition of max itself, we get this inequality, right? So from a property of Riemann integrals that we already have proved, we have this. Okay. Now because this is already greater than this, so automatically this will also be greater than this. So all these things finally mean that we can, if the need be, if f plus underscore becomes negative at some places, we do not consider this anymore. We replace this with this, which is non-negative, and it has all the properties that f plus underscore also has. Or in other words, we can simply write that because of these things, this arrangement, Without loss of generality, we can assume that f plus underscore itself is non-negative. Okay, so now because of these things, we are justified in assuming such a thing without losing any generality. So let's continue from here. So we can assume without loss of generality that this is greater than or equal to 0 for all x belonging to I. Similarly, you can also assume without loss of generality that f plus bar, that other function which majorizes f plus, is less than or equal to that upper bound m1. If not, then you can replace f plus bar by minimum of f plus bar and m1. Okay, you should be able to figure this out. I am not going to say anything more on this. Instead, I simply write what the author has written. Similarly, we can assume without loss of generality that f plus bar of x is less than or equal to m1 for all x belonging to I. Let us now write what the things are that we now have. So, we now have these inequalities. Due to our conditions, now we have this, and already we had this and this, and additionally we now also have this for all x belonging to I. And whatever we have done for f plus will have an exact similar thing for g plus also. Similarly, there exist PC functions g plus underscore from I to R and g plus bar from I to R, such that, let's write these inequalities first for these functions. For all x belonging to I and the integral inequalities. I always kind of get confused while writing these integral inequalities. I again have to think every time because I have not really memorized the pattern in which they appear. So let me again think. Well, the first one we wrote for f was what? It came from the lower Riemann integral, right? So the lower Riemann integral is least upper bound. Least upper bound, that means if we add, not add. Least upper bound means if we subtract epsilon from it, then it is no longer an upper bound. Okay. That means if we subtract epsilon from it, it is no longer an upper bound. Minorizing, yes. Whereas we have this. Things may become very confusing due to the choice that the author has made for these notations. You are having underscore, bar, you also have, it's coming next, upper bound and lower bound and, upper integral and lower integral, which also use the bar and underscore notation, so you have to be very careful with these things. Okay, so we have set up whatever we could set up with the functions f plus and g plus and our chosen epsilon. Okay, now let us see what we can next say about this product. Say you take the product of f plus and f plus underscore and g plus underscore. What can you say then? You see, you may be wondering why we needed the non-negativity condition here. Now you will realize why we need the non-negativity condition. That's because what now I am going to do, I will multiply these inequalities. Won't really write m1, m2, but will multiply f plus underscore, g plus underscore, and with f plus I will multiply g plus, because that's what we need, no, f plus g plus. And I will also multiply g plus bar and f plus bar. And after multiplying also, in order to restore the sense in which we have the inequality, so that nothing gets reversed and mixed up, we need non-negativity. That is why. Because otherwise there is no guarantee that you continue to have these inequalities if these lower functions fail to be non-negative at some point. Okay. Now, but before we write the inequalities though, let us also note this. F plus underscore times g plus underscore and f plus bar times g plus bar are both PC functions. Because when we take products of PC functions, you get PC functions again. Also, now we write that thing. F plus underscore x times g plus underscore x is less than or equal to f plus x times g plus x, which is less than or equal to f plus bar of x times g plus bar of x for all x belonging to I. So not only are these two functions PC functions, but this one minorizes f plus g plus, and this one majorizes f plus g plus. So what can you then write? For all minorizing functions, the least upper bound of their integrals is by definition the lower Riemann integral of f plus g plus. And for all majorizing functions, the greatest lower bound of their integrals is the upper Riemann integral of f plus g plus. So, what will be the integral of this? F plus underscore g plus underscore. Since it's a minorizing function, this will be less than or equal to the lower Riemann integral of f plus g plus. You see how confusing things can become. You have underscores here, you have underscore there. This is what I was talking about back then. And we can continue, no? I mean, I can write here itself, which is less than or equal to the upper Riemann integral of f plus g plus. Which in turn is less than or equal to the integral of the majorizing function. So from these inequalities, we can next write this. Thus, we have, now if you subtract the lower Riemann integral from the upper Riemann integral, due to this middle inequality, that will be non-negative. Minus the lower Riemann integral. Now the upper Riemann integral is, this one is less than or equal to this. So let's continue by writing less than or equal to the integral of f plus bar g plus bar. But the lower Riemann integral is greater than or equal to this. However, its negative will be less than or equal to the negative of this then. So, minus integral of this. Now, these are just integrals, ordinary integrals. You see, these are upper and lower integrals. These, however, are integrals actually of functions which you already know are Riemann integrable. That is why this can be written as a single integral. Now we are going to concentrate our focus on this difference. Let me continue from there. Now, f plus bar g plus bar minus this. it can be written as f plus bar g plus bar minus f plus bar g plus underscore, but to compensate for that you also write plus f plus bar g plus underscore, and we already have this f plus underscore g plus underscore. Okay. Now you think of the first two terms. From them you can take out this. You then have this plus similarly the second term will be this. Second means in this way of writing. All right. So far we have used non-negativity, I mean inequalities on that side. But what about the functions being less than m1, less than m2? Now we will use those bounds, upper bounds. So you know that f plus bar is less than or equal to m1. So we can write this inequality. See, I was going to write minus. There is no minus. We have only plus. And g plus bar is, underscore is, hold on, have I made a mistake? See, here I wrote minus. Yeah, something was amiss. But if I have, let me just see if I am really getting something wrong. F plus bar is less than or equal to m1 and g plus underscore is less than or equal to m2. Well, that is also true, because g plus underscore is first of all less than or equal to g plus. Then g plus is less than or equal to g plus bar, which in turn is less than or equal to m2. So obviously this one is also can be replaced by m2, and these things are so confusing. I mean, already the things are confusing, but the notations are such that you can easily make mistakes. But still there is something that needs to be justified. You see, whenever you have equality, an inequality, and you need to replace something by a bigger thing, but something else is multiplied, you need to make sure that whatever the other factor is itself non-negative. Why? Why? Because of this. You see, let's take the example of this first one. We know that actually how are we getting that this is less than or equal to this? We know this inequality, and we have multiplied both sides by this, and that's how we have obtained that inequality. So because we are multiplying by something, obviously we need to make sure that this is positive, or if that cannot be ascertained, at least non-negative, that it can be 0 at places but elsewhere it's positive. Is it really non-negative? Yes. How? Well, that comes from this. g plus underscore is less than or equal to g plus, which is less than or equal to g plus bar. So at any x, the value here is less than or equal to the value here. So this difference at any x is non-negative. So the function is non-negative. Okay, so that's why this is justified. Similarly, this one is also justified because f plus bar minus f plus underscore is non-negative. Alright, so now that we have this inequality that this is less than or equal to this, so we can integrate, ordinary integration. Do not forget that the functions involved now are all piecewise constant functions. Okay, so no question of not being integrable, everything is integrable. So using ordinary properties of integrals of PC functions, now the inequalities can also be written involving integrals. So the integral of this minus this is less than or equal to the integral of this. However, m1 of course can be taken out and you have this plus m2 Now, if you go back to those four inequalities involving integrals of f plus, g plus and the integrals of these piecewise constant functions, you will see that this difference, this integral, which is actually the integral of this minus integral of this, is less than 2 epsilon. Okay, it's coming from those inequalities. And that is why this is less than or equal to m1 times 2 epsilon. Similarly, this integral, which is integral of this minus integral of f plus underscore, is also less than or equal to 2 epsilon. However, we have already got there that this integral is greater than or equal to the upper integral minus lower integral. Hence, 0 less than or equal to this minus lower integral ultimately becomes less than or equal to this. Since epsilon is arbitrary and m1 and m2 are both positive, so you can choose any epsilon as small as you want, and because of that, this quantity which is trapped in the middle of these two things has to be equal to 0. Due to this inequality, it can either be 0 or positive. But if you choose it to be positive, then a value of epsilon can be given so small that this second inequality will be violated. And that is why this middle term cannot be positive, so it has to be equal to 0. In words, we simply write, since epsilon greater than 0 is arbitrary, must be equal to 0. So lower integral is equal to upper integral, and thus f plus g plus is Riemann integrable. This is where the proof ends. Ends means there then the author says that the other three, f plus g minus all those things, can also similarly be shown to be Riemann integrable. That we will address. Okay. In the next upload means the next post will be a community post, because we will start solving exercise problems. So there all those unresolved issues will be resolved. And here the proof ends for us, and this section also ends. I mean the theory part ends. After this we have the next section where, you see, what have we done so far with integration? We first of all defined a full theory of integrating piecewise constant functions. We then defined proper Riemann integral for bounded functions. And we have now derived some properties of integrability. That is, if integrable functions are given, we can create algebra, that is, we can add them, multiply them, take maximum, minimum, those things, and produce more integrable functions. But is that all? No. I mean, we need to at least show that besides the piecewise constant functions themselves, there are other bounded functions which are also Riemann integrable, because otherwise, what is the point of doing all these things? If you cannot produce an example of an integrable function that is not piecewise constant. So that thing will be rectified in the next section by showing that continuous functions are also Riemann integrable, need not be piecewise constant. Okay, so that will enlarge the class of integrable functions. But anyway, that's just it for tonight. And tomorrow we have number theory, and yeah, luckily I can do both, no? Because tomorrow in class 11 mathematics I have to solve exercise problems, and in number theory also I have to solve exercise problems. So we will do both of that. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.